A z-score tells how many standard deviations a data value is away from the mean. It's a way to measure how extreme or unusual a value is. For example, let's take this chart of information about the mean and standard deviation of the heights of US adults, women and men. Sorry, I don't have data on the mean and standard deviation of the heights of non-binary US adults. Let's compute the z-score of a woman who is 70 inches tall. That's 5 feet 10 inches. The z-score takes the data value, x, and subtracts the mean, mu. Then it divides by the standard deviation, sigma. So here we have 70 minus 64.1 divided by 3.8. That gives 1.55. So a woman who's 70 inches tall is 1.55 standard deviations above the mean for women in the US. Try using that same process to compute the z-score of a man who is 73 inches tall. That's 6 foot 1 inch. Here we have a z-score of 73 minus 69.6 divided by 3.0. So that gives 1.13. We can use these z-scores to answer the question, who is taller relative to their peers, the 5 foot 10 inch woman or the 6 foot 1 inch man? We can think about the z-scores as a way of rescaling both of the distributions, the heights of women and men, and putting them on the same graph, so they're centered at the same place. We'll call it mu to represent the mean of whichever distribution we're talking about. Well, the 6 foot 1 inch man shows up here, 1.13 standard deviations above the mean. And the 5 foot 10 inch woman shows up here, 1.55 standard deviations above the mean. So the 5 foot 10 inch woman is farther from her group's mean as measured in standard deviations. So she's taller relative to other US women compared to the man relative to other US men. To see an example of where z-scores are useful, let's suppose that you're on UWEC's admissions committee and you're trying to decide who to admit for the entering class of next year's first-year students. Let's say you're down to the last spot in the entering class and you're trying to decide between two really good candidates that have equally good credentials on a lot of aspects. They've taken exactly the same classes in high school, they have equally good extracurriculars, and equally good essays. So you need to decide between these two candidates based only on their standardized tests. But the problem is, one of them took the ACT and the other one took the SAT. So ACT scores have a mean of 20.8 and a standard deviation of 4.8. And Jermaine got a score of 28. SAT scores have a mean of 1,026 and a standard deviation of 209. And Tanya got a score of 1,320 on the SAT. So whose score was better? Take a moment to try using z-scores to answer this question. For both students, we compute the z-score by taking their score on the standardized test, subtracting the mean of scores on that test, and dividing by the standard deviation of scores on that test. So Jermaine ends up with a z-score of 1.5, and Tanya has a z-score of 1.4067. That means that Jermaine is more standard deviations above the mean for the test that Jermaine took compared to Tanya. So if we really have only one spot left in the entering class, then Jermaine should get the spot and Tanya goes on the wait list. Because z-scores are a measure of how unusual or extreme a data value is, we can use them to assess the strength of evidence against the null hypothesis as an alternative to using p-values. Here's the way this works. We take our usual formula for a z-score, and in place of x, the data value, we plug in the statistic we got from our sample. For mu and sigma, we plug in the mean and standard deviation of the null distribution. We can get these either from the applet, as we'll see on the next slide, or using a theory-based approximation, which we'll talk more about in the video on the binomial distribution. Let's use the z-score, also known as the standardized statistic, to investigate whether the death rate for heart transplants at a particular hospital is worse than the national death rate for heart transplants, which is 15%. So we're investigating these hypotheses. The null hypothesis is that pi equals 0.15, where pi is the long-run proportion of heart transplant patients at St. George's Hospital who die. And the alternative hypothesis is that pi is greater than 0.15. The data from a sample of 361 heart transplant patients at St. George's was that 71 patients died. That's a sample proportion of 0.1967. So when we plug this into the one proportion applet, we get a null distribution that looks like this. And I've highlighted the repetitions that were at least as extreme as 0.1967, giving a p-value of 0.009. So very strong evidence against the null hypothesis. If we check the box in the applet that says Summary Stats, the applet will display the mean and standard deviation of the null distribution. So the mean and standard deviation shown in this histogram, actually a dot plot, shown here. So now we can use our formula for the z-score to take our statistic, 0.1967, and subtract the mean, which is 0.15, that's exactly the value from the null hypothesis, and divide by the standard deviation. And we get a z-score of 2.59. Finally, we compare our z-score to the following table to assess the strength of evidence against the null hypothesis. In this case, our z-score was above 2, so we have strong evidence against the null hypothesis. That doesn't quite agree with the results from our p-value, 0.009, which said that there was very strong evidence against the null hypothesis. So the results from the z-score and the p-value won't always agree entirely, especially when you're doing a one-sided test. But in this case, the difference between strong evidence and very strong evidence with a p-value that's very close to 0.01, the threshold for very strong evidence, I would say that these two results largely agree about overall there's evidence against the null hypothesis. Here's a table showing the relationship between z-scores and p-values in the strength of evidence against the null hypothesis. We'll talk more about why these z-scores correspond with these p-values in the video on the empirical rule.